Hello and welcome to this video where today we're looking at nuclear fission and nuclear fusion, and we're going to start off by looking at nuclear fission. So as you remember from GCSE, nuclear fission is defined as the splitting of an atomic nucleus, and this can happen basically in two ways. Either it can happen spontaneously, in other words we do nothing to it, where we have a large nucleus and it just basically splits into two. This is a very rare process. Alternatively, we can have induced fission. Now induced fission is basically we make the thing happen. So induced basically means we're making it happen. So this is the kind of diagram that you will have seen from GCSE. What I've done here is this is kind of like at the start of the process, this is the end, so you can kind of think of time moving downwards in this diagram. So what this shows is, for example, we've got a uranium-235 nucleus, for example. And what we do is we take a neutron and we fire it inwards, as this arrow shows. The neutron will move towards it and then it'll be absorbed by this nucleus. So what's not happening is that the neutron comes in and basically smashes this thing apart. It actually moves fairly slowly towards it and it gets absorbed by this nucleus. So now we've ended up with a bigger nucleus, so we've got uranium-236. Now uranium-236 is even more unstable than uranium-235. Now what's helpful to kind of think about is actually what's going on inside this nucleus. Normally we think about nuclei as being very static objects. So the protons and neutrons are basically just sat there. That's actually not true. The protons and neutrons are actually kind of moving around all over the place and kind of jostling around. And so when we've put our neutron into here, these things jostling around all over the place, and although it's generally a spherical shape, it'll kind of gradually move into different shapes and all sorts of and make all sorts of different configurations. One kind of configuration it can make is something like this. So the things are moving around so much that you end up with kind of a narrow part here. Now, if you think about it, the thing that's holding this thing together is the strong nuclear force, and the strong nuclear force is only a short range force. So these two things, these two protons, are actually repelling each other, but they're also holding on to each other because of the strong nuclear force. But this proton and this proton are repelling each other because of the electrostatic force, but they're not attracting each other because the strong force is only a very short range force. To keep this thing together, we actually need some more particles here and here so that the strong force has kind of got enough particles there to hold it together. So this thing now hasn't, and so therefore can't hold itself together, and so he's going to split into two. And that's what happens here. So we've gone from a big nucleus, it's jostled around, it's come to a point where there's kind of a narrow section between the two things. It can't hold itself together anymore, and so it splits into two. So we end up with two daughter nuclei, and also two, or as we've shown here, 2 or 3 neutrons also released in this process as well. And also, vitally, because it's what we want out of this thing, there's also some energy given out too. And the energy is in the form of kinetic energy of our, so the kinetic energy of our neutrons and also our nuclei too. So all of these things will be moving around. So these two nuclei and these neutrons are moving around, and the kinetic energy that we get out of it, we can basically extract that, and then we can use it in our nuclear power station, for example. So that's the process of nuclear fission. The kind of questions you get asked if it was an exam. So we've been given an equation that shows induced fission. So we've got our uranium nucleus and we've added to it a neutron. At some point later on, we've split it up into these two nuclei and something else. Well, we know that neutrons are emitted in this case as well, and we know that neutrons have got a mass number of 1 and atomic number of 0. We just need to know how many are actually emitted in this particular case. So the bottom numbers don't help us at all, because if we look, what we should have is that the number we start off with on this side equal the number that we finish with on this side. Well, 56 add 36 basically give us 92. So the bottom line doesn't help whatsoever. The top line, however, does, because we're starting off with 236 up here, 235 add 1, and that's gone to 144 and 90. So that's gone to 234 plus something else. So we've got 236 there, 234 here, so we need to have 2 here. So actually in this process, 2 neutrons have been released in this process and some energy. Now we can work out how much energy is actually released in this process, because if we know the binding energy of this thing and we know the binding energy of these things, the difference in the binding energies, the difference in those energies are the amount of energy that's been released. We don't have to worry about the binding energy of our neutrons because neutrons are single particles, so they have no binding energy. So essentially, when it comes to looking at the energies of these things, we can ignore these. So we need to work out the difference between the total energy on the total binding energy on this side and the total binding energy on that side. So to start off with, let's have a look at uranium. Well, we know that the binding energy per nucleon is 7.59 MeV. And if we multiply that by the number of nucleons that we've got, in this case 235, we can work out the total binding energy on this side. And if we do that, we get 1783.65 MeV. So that's how much binding energy we started off in the first place. We can then work out how much binding energy we finished with. So because we know that the binding energy per nucleon of this thing was 8.5, and we've got 144 nucleons altogether. So the total binding energy of that nucleus is 1224 MeV. We can do the same thing for our krypton nucleus. So we've got 8.5. This time we've got 90 nucleons, which gives us 765 MeV. So if we add these two things together, it gives us the total binding energy on this side. If we do that, we get 1989 MeV. So simply to work out how much energy is released in this, we just work out the differences in the energies. So we have 1989 minus 1783.65, and if we do that, we get 205 MeV. So we've got 205 MeV of energy released every single time that this fission process happens. So that's nuclear fission. Looking at nuclear fusion is potentially more simple. So nuclear fusion is the joining of two atomic nuclei, and they're generally small nuclei. We'll see why in a second. Now, you remember again from GCSE that in order for this process to happen, we need really high temperatures, because what's actually happening is this nucleus is positive overall, this nucleus is positive overall, and so when we try and push them together, they repel each other. Because they have the same charge. So we need really high temperatures, because high temperatures means high kinetic energy, and high kinetic energy means they're moving really quickly. The faster they move, the closer they can come together. When they get in the range of the strong nuclear force, that will then be strong enough to overcome the electrostatic repulsion, and it will pull them together and it will join together. So here we've got, for example, an isotope of hydrogen. So we've got deuterium, we've got another isotope of hydrogen, we've got tritium, and if we can force these things together, essentially we could make, for example, helium, and also release a neutron in that process as well. So that's basically nuclear fusion. You start off with two small nuclei, you join them together, you get a bigger nucleus, and very, very often kind of like a single particle or a couple of single particles left over. Both of these things again will be moving, and so we'll have kinetic energy, and if we can kind of extract that kinetic energy, then we could use it again in a power station, for example. So this is a very similar question to the one we were asked before. Here again, so this is an equation version of the picture we've just seen. You've got deuterium, so an isotope of hydrogen with one proton and one neutron. Tritium, an isotope of hydrogen with one proton and two neutrons. When you put those together, you get helium and a helium nucleus, and you also get a neutron left over as well. So again, we want to know the energy released in this process. This time it's very slightly different, because instead of having the binding energies per nucleon, we're actually given the masses of these things. But the process is exactly the same as we saw in the last video. If we can work out the mass defect, in other words, the difference in energy between this side and this side, then we can go on and we can work out the energy that's released. So first of all, let's have a look at the mass we started with. So the mass we started with, we simply add the mass of that and that together. So we have 2.014102 plus 3.016050 gives us 5.030152 atomic mass units. And I'm going to keep all of these decimal places to make my answer as accurate as I possibly can do. That's a 0. So that's the mass that we started off with. The mass that we finish with, well, the mass of our hydrogen nucleus is 4.002603 plus the mass of our neutron, which is 1.008665, and that's equal to 5.0112 268. Now, one thing that's probably important to say is that this time, because we're looking at masses, we have to include the mass of our neutron in this one. In the last question, when we looked at nuclear fission, because we were given the binding energies, we didn't have to consider the neutrons. In this case, we do. So if I take these two things and we work out the difference between them simply by taking them away, we end up with a mass defect of 0.0188884 atomic mass units. So there's a difference in mass, and because there's a difference in mass, therefore there's a difference in energy. So I'm just going to use the conversion factor to convert atomic mass units into MeV, so we know that 1U is equivalent to 931.5 MeV. So if I just multiply this thing by 931.5, it'll tell me the energy I've got in MeV. So E is equal to the mass defect, 0.0188884, and multiply it by this conversion factor, 931.5, and that equals 17.6 MeV. So every time this happens, 17.6 mega electron volts of energy are being released in this process. So we've got two different processes. We've got fission, which is the splitting of an atomic nucleus, but we get energy out. We've got fusion, again, it's the joining of nuclei this time, but again, we get energy out. So when does this happen? Well, we saw in the last video that we could draw basically a graph of the mass number of all of the different nuclei against the binding energy per nucleon. And we got a graph approximately like this. Now, because we know that this thing here is the most stable, this thing here has got the highest binding energy per nucleon. If we take two small nuclei and we join them together, then the binding energy of the resultant nucleus increases. And if the binding energy goes up, what's basically happened is that means the nucleons have moved closer, so the potential energy has gone down and we get energy out. What you can't do is you can't get energy out from nuclei by fusing two really big things together, because if you fuse two big things together, then actually what happens is the binding energy will decrease, which means that essentially the nucleons would have to have moved apart, which means that we would have had to put some energy in to do that. So you can only release energy through fusion between these 2 points here. And very, very similarly, you can only release energy through fission by splitting large nuclei into smaller nuclei until you get to this point. If, for example, you took a helium nucleus and you tried to split that apart into two hydrogen isotopes, then what you'd find is you'd have to actually put some energy in to do that. Your energy wouldn't be released. This is basically the two processes are very akin to each other. So for example, let's take fusion for example. Basically what happens is you fuse your two light nuclei, the binding energy increases so that you end up with a higher binding energy per nucleon than you did to start off with. This essentially means the nucleons have moved closer together, so the thing's more stable. That means the potential energy has gone down, so you get energy out. So you could potentially be asked why, in terms of this graph, why energy is released in fission and fusion. So this is an example from the exam board. They basically said, and these are the four things that you need to know. And so we're going to mention both fission and fusion in our answer. So for example, energy is released when the binding energy per nucleon is increased, which is basically what we've just said. You then can describe what happens in fission and fusion. So fission, a large nucleus splits, fusion, small nuclei join together. As we've again just said, the most stable nuclei are at the peak, and so fusion occurs on this side and fission occurs on this side. So you've basically described why fusion happens with small nuclei and why fission happens with large nuclei. So that's nuclear fission and nuclear fusion. Thank you very much for watching, and I'll see you again soon.